In this lecture, we are going to introduce Padé approximations for continuously differentiable functions, state the required conditions of a Padé approximation, and derive the system of equations for finding the coefficients of Padé approximations. We start with a function f that is continuously differentiable on the interval from x equals a to x equals b with a less than 0 less than b. A Padé approximation for f of x is a rational expression which we call r of x. R of x is equal to the quotient of two polynomials p of x and q of x. We set p of x equal to the sum of p sub 0 all the way up to p sub n times x to the nth power, while we set q of x equal to the sum of 1 q sub 1 times x all the way up to q sub m times x to the nth power. Observe that q sub 0 is equal to 1. And q sub 0 being equal to 1 ensures that r of x is continuous on an open interval of positive length around x equals 0. The degree of the Padé approximation is the sum of the degrees of p and q, and so the degree of the Padé approximation is m plus n. So to find the Padé approximation, we need to find the coefficients of p of x and q of x. One requirement that we impose on the Padé approximation is that each derivative of f at x equals 0 from the 0th derivative to the m plus nth derivative equals the corresponding derivative of r. This leads us to examining the degree m plus n Maclaurin approximation of f of x. We call this Maclaurin approximation a of x. Let a of x be the sum of a sub 0 all the way up to a sub m plus n times x to the m plus nth power. Of course, a sub k is equal to the kth derivative of f evaluated at 0 divided by k factorial for k equals 0 to m plus n. We obtain the Padé approximation by assuming that a of x is identically equal to r of x, or that a of x minus r of x equals 0, or that a of x minus p of x divided by q of x is identically equal to 0. We write a of x minus p of x divided by q of x as a single fraction and obtain this equation. Because q of 0 is equal to 1 and q is a continuous function, q of x must be non-zero over an open interval of positive length around x equals 0. And so based on our assumption that a of x minus r of x is identically equal to 0, the numerator of the left side must be identically equal to 0 over this open interval around x equals 0. Expanding the numerator, the resulting constant term is 1 times a sub 0 minus p sub 0, and so a sub 0 should equal p sub 0. The first degree term is equal to q sub 1 times x times a sub 0 plus 1 times a sub 1 times x minus p sub 1 times x. And so q sub 1 times a sub 0 plus a sub 1 should equal p sub 1. The second degree term is q sub 2 times x squared times a sub 0 plus q sub 1 times x times a sub 1 times x plus 1 times a sub 2 times x squared minus p sub 2 times x squared. And so q sub 2 times a sub 0 plus q sub 1 times a sub 1 plus a sub 2 must be equal to p sub 2. As an exercise, one can show that q sub m times a sub 0 plus q sub m minus 1 times a sub 1 plus all the way up to a sub m must be equal to p sub m. And up to the m plus nth degree term, q sub m plus n times a sub 0 plus q sub m plus n minus 1 times a sub 1 all the way up to a sub m plus n should equal p sub m plus n. And so the sum from I equals 0 to k of q sub k minus I times a sub I should be equal to p sub k for k equals 0 to m plus n. This set of equations guarantees that all the terms of degree up to m plus n from the numerator of a of x minus r of x cancel out. And so the minimum degree of the numerator, which is a of x q of x minus p of x, is at least m plus n plus 1, so that we should be able to factor out x raised to the m plus n plus 1th power from the numerator. Therefore, we should be able to write a of x minus r of x as the product of x raised to the m plus n plus 1 power, and a continuously differentiable function that we call h of x. One can show that the kth derivative of x raised to the m plus n plus 1 power times h of x is 0 at x equals 0 for k equals 0 to m plus n. We leave the details of the proof of this fact as an exercise for the viewer. And so it follows that the kth derivative of a at x equals 0 is equal to the kth derivative of r at x equals 0. And since a of x is the degree m plus n Maclaurin approximation of f of x, the kth derivative of a of x at x equals 0 is the kth derivative of f at x equals 0. Therefore, the kth derivative of f at x equals 0 equals the kth derivative of r at x equals 0 for k equals 0 to m plus n. So that we have just shown that the Padé approximation satisfies the requirement that we had imposed on it at the beginning of this lecture. Since the highest degree term of p of x is p sub n times x to the nth power, we require that p sub n plus 1 all the way up to p sub m plus n be 0. And since the highest degree term of q of x is q sub m times x to the mth power, we also require that q sub m plus 1 all the way up to q sub m plus n be 0. And so combining these last set of equations with the equations for the lower order coefficients, we have the system of equations for the coefficients of the Padé approximation of f.